Namaskar friends, I welcome you all in this class of structural analysis. Today we are going to discuss analysis of structures by energy methods. Friends, energy methods are quite important, and from very ancient times energy methods have been used to analyze the structures. These methods are very general in nature, and long back since 4th century BC they have been used. I will give you the concept of strain energy. If any structure which is linearly elastic, it obeys Hooke's law, and if it obeys Hooke's law, then if any force or system of forces are applied to the structure, then the strain energy is stored in the structure because of the axial forces, shear forces, bending moments and twisting moments. And this is because the deformation inside the structure which is elastic in nature. So that's why we call it that energy is stored in the member. So if you say what is the strain energy stored by a member, this is equal to amount of the work done by the external forces to produce the deformation. So friends, we will see one by one that how the strain energy in various structures due to various types of forces are stored. So let us derive strain energy due to axial forces. So friends, suppose this is an element of length say ds, and we are applying axial force say F. On this element. So what will be the energy stored in this element? This will be equal to say the average force F by 2 multiplied by the deformation delta in this element ds. Why we are taking this average force? Because as soon as we start applying force on the element, the elongation starts and the energy is stored. So what happens that the axial force increases from 0 to F for an elongation from 0 to delta. So the work done will be equal to this area, that is the force I can take F by 2 into delta or F multiplied by delta, and its half energy will be stored. Now what is delta here? You know from your classes in strength of material. from a strength of material you know that modulus of elasticity E is equal to stress upon strain, and stress is F divided by A, where A is the area of cross section of the member, divided by strain. Strain is delta divided by length of the member. In this case, this is ds. So if you calculate delta from here, delta will be equal to Fds by Ea. So if you put this value of delta here in this calculation, so du will be equal to F by 2 multiplied by Fds divided by Ea. So this becomes F square ds divided by 2Ea. Now if we want to calculate the total strain energy stored in a member due to axial force, then it will be equal to U will be equal to integration from 0 to L F square ds divided by 2Ea. Similarly, friends, we can calculate the strain energy stored by a member when shear force is applied.